Okay, here we have a related rates problem. We've got a conical tank, vertex down, it's 10 feet across the top, it's 12 feet deep. We've got water flowing into it at a given rate, and we need to find the rate of change of the depth of the water at a particular instant. Okay, so our first step, of course, is to draw a picture capturing what's going on here in this problem. Okay, so we do that. Now notice, I'm not labeling anything on this picture just yet. I'm going to hold off on that for a minute because I need to first ask myself the question, in this problem, what rates are known, given, and what rates are unknown? What rates do I seek to find? Okay? Well, as for the known rates, recall we have water flowing into the tank at a rate of 10 feet cubed per minute. Okay, so that's a given or known rate. So let's write that down. Okay, so we have the water coming in at this rate. This is measured, notice, in feet cubed per minute. So this is a rate of change in feet cubed, which measures volume, per unit time. As such, this is the value of a derivative, namely the derivative of volume with respect to time. You can always look to the units here to figure out what derivative you have for a given rate. So let's call this dv dt. Now notice that we really should check one other thing here. The water is flowing into the tank. So in other words, the amount of water in the tank is growing. It's increasing. What does that say about the derivative value in terms of its sign, positive or negative? Well, of course, it has to be positive if we're increasing. And that doesn't require a change here, but had this said the water is leaking out of the tank at this rate, then the water would have been shrinking, and then we would have made this negative. Okay, so it's a question that needs asking, but it doesn't require any further action in this case. Now, are there any other known rates given to us in the problem? Well, no. So let's move on to the unknown rates. What rate are we trying to solve for? Recall, we need to find the rate of change of the depth of the water. The depth of the water, of course, being the distance from the surface of the water all the way down to the bottom. So let's label that. And if we call that distance h, then the rate we seek must be dh dt when we write it as a derivative. Okay? Now, I want to continue to flesh out my picture here with the other information that's presented to me in the problem. But as I do so, I need to keep in mind the question, or questions, what is actually constant over time versus what is true only for an instant of time? Look, back in my problem, I've got several different numbers here. I have the tank is 10 feet across. We have it 12 feet deep. I have another 8 feet deep here. Okay, but which of these numbers is actually constant over all time? Well, the tank's width across the top is not likely to change as time moves forward. So that's a true constant. So let's label that accordingly in our picture. Similarly, the depth of the tank being 12 feet, that's not likely to change over time either, so let's label that. However, this 8 feet deep, this is the depth of the water, but it is only valid in a particular instant. Of course, water is filling up the tank, and so the depth should be constantly changing, and in fact, constantly growing. So rather than put this information on my picture, you see I want my picture to be valid for all times t, I'm going to put this information kind of off to the side in its own special location. Okay, so we make a note down here that h is 8 feet, that's the depth of the water, in the instant that we're concerned with. Okay? Now, time to ask the big question. Can I find a relationship, and by relationship I mean an equation, involving just the important variables? And what are the important variables? They're the variables for which you either have a known rate or you're looking for a particular rate. Okay? So we're talking about V and H here. It may be that we'll have to introduce some additional variables to finish off this problem. But if I don't have some known rate information about those variables, or I'm not seeking the rate of change of those additional variables, I don't want them appearing in this relationship, in this equation. Okay? So I need an equation involving just V's and H's. The volume of water, the volume of this blue cone, not the overall cone, and the depth of the water, or the height of the cone. Well, it may not be immediately obvious what that equation should be, but perhaps I can get closer to it by starting with something I do know. I do know something about volume for cones. You might recall from geometry that volume is 1/3 the base area. Of course, here the base is this circle, times the height of the cone, h in this case. Now, we have an equation that does indeed involve V's and H's, but not only V's and H's. It also involves this B, and this B is not a constant. This B is changing over time. As water fills the tank, this circle rises and gets larger. So I need to get rid of this B. Now, this is the area of a circle, so maybe that sparks something in your mind, something like pi r squared, the area of a circle. Let's make that replacement. Okay, so now we have another equation which has V's and H's in it, but unfortunately, just like the one above it, we also have an unwanted variable. We don't want to see this r. Again, as time goes by, r is changing. It's getting longer and longer and longer as that circle gets larger and larger. So again, I want to get rid of this r. I want to replace it with something involving only V's and H's. Is there some sort of relationship between the radius and V's or H's? Well, this is where we have to get a little bit inventive. Do you see that this blue cone of water and this black cone that represents our tank are actually similar three-dimensional solids? So their dimensions should be proportional to one another. Perhaps to see this more clearly, imagine drawing a line from the tip of the cone to the center of this top circle, then drawing in the corresponding radii up here, and notice in the two resulting right triangles that we form, because they share a common angle, these two triangles must be similar. Let's redraw this pair of triangles down here where we can see things more clearly. Okay, and notice that this top side here, which is this radii, or radius, must be half of the diameter of the large circle, and so that would be 5. This side of the triangle right here is the radius that we're talking about when we write this r. And then, of course, the heights h and 12 come down directly. Now, appealing to the proportions in similar triangles, we can say something like this side is to this long side as this little guy is to this little side. Or in other words, 5 is to 12 as r is to h. So we've found a relationship between r and h. And that's useful because we can exploit this relationship to solve for r in terms of h. And that will give us something to substitute here to eliminate the r's. So let's do that. Let's solve for r. Of course, that's quick. We just multiply by 12h to clear the fractions and divide by 12. And there's our expression for r that I can now plug in here. Let's slide things up a little bit so we have some more room. So making the substitution, we have this. this is what we were after. This is an equation, a relationship, that involves only V's and H's, and nothing else other than constants. Now it's going to be useful, and you'll see why in about 2 seconds, to go ahead and simplify this, to tighten this up, to make it differentiation friendly. Okay, notice you have a couple of constants here at 1/3, this 5/12 squared, you've got a pi here. Those can all be brought to the front, and then you have a couple powers of h squared and h, that can be combined together. So let's go ahead and do that. Okay, so now we have this nice tight relationship between V's and H's. This is a relationship between the important variables, but what I really need is a relationship between the rates, dV over dt and dH over dt. But I can introduce these two rates over here by differentiating both sides implicitly. That's why we simplified this and tightened it up and made it differentiation friendly. Okay? Notice what happens when I differentiate the left and the right sides with respect to time. Of course, on the left, the derivative of v with respect to time is simply dv dt. Over here on the right, of course, this is just a constant multiplier, so it comes down. And then I have h cubed, so that's 3h squared. But remember, just like v was a function of time, so is h. We're differentiating implicitly with respect to time, so we have to tack on a dh dt on the end by the chain rule. So now we got what we're after. We have a relationship between the rates. The rates have been related here. Now the question is this all I need? Do I know enough to solve for the unknown rate? Remember, we're after dH dt. So this is unknown. Do I know h? Do I know dV dt? Well, dV dt is 10 feet cubed per minute. That's true at all times t. And h, while I don't know it for all times t, I do know it for a given instant. It's 8 feet at the instant I'm interested in. So I'm free to plug those values in here and then solve for dH dt. Okay, so I'm going to write this down here so I can scroll this thing up a little bit. Okay. There. We got enough room now. Now, like we said, let's go ahead and plug this information in up here, plug in what we know, and solve for the unknown rate. Okay, so 10 goes in this spot. There we go. 8 goes in this spot. We square it right here. And now we effectively have a linear equation in terms of this unknown dH dt. So we solve it in a very predictable way. We simply divide both sides by this giant mess over here. Of course, before you do that, you might want to cancel the 3's here. A little simplification of opportunity. All right, so doing the division, we end up with, and then we notice we can cancel a 5. And then proceeding on with the rest of the arithmetic here, we finally get, as the value for dH dt, 9 over 10 pi feet per minute. And that's our answer. Now, a quick check. Remember, way back up here, we noticed that the depth of the water, which is represented by h, should be increasing as water gets poured into the tank. And so the derivative of h with respect to t should be positive or negative. Well, of course, it should be positive since it's increasing. And notice the answer we got was positive. Okay, so that's one little quick thing you can check just to make sure nothing went wrong. It's not a guarantee that you'll catch a mistake if it's there, of course, but it does help. Okay, that's it.